On December 7, 1941, as smoke still rose from the burning ships in Pearl Harbor, Japanese Admiral Isoroku Yamamoto wrote prophetic words in his diary. "I fear all we have done is to awaken a sleeping giant." But even he could not imagine the scale of what would come next. Picture this. In a single day, the U.S. Navy lost 18 warships, including 8 battleships. 2,403 Americans were killed. Another 1,178 wounded. The Pacific Fleet lay at the bottom of the harbor, reduced to heaps of twisted steel and ash. Now, imagine the reaction of Japanese admirals when, only 1 year later, just 12 months, they saw an American armada of more than 100 new warships approaching their shores. "Impossible," whispered the commander of Japan's combined fleet. But it was more than possible. It was reality, and it would forever change the course of World War II. How could a nation rise from the ashes of such a devastating defeat and in a single year create the most powerful naval force in human history? This question tormented Japanese commanders throughout the war and continues to fascinate historians today. The story of America's industrial mobilization in 1942 is not just about ships and weapons. It is an epic of national transformation, of millions of ordinary people who, in a matter of months, learned to build the most complex war machines of their age. It is the story of women who took up welding torches, farmers who became engineers, and teenagers who worked 16-hour shifts for victory. On December 7, 1941, America had a navy of 790 vessels of various classes. After Pearl Harbor, that number dropped sharply. But by December 1942, exactly 1 year later, the U.S. Navy counted more than 2,000 ships. By the end of the war, the number would rise to 6,768. But how did this happen? What secrets lay behind this incredible industrial miracle? And why did the Japanese so drastically underestimate their enemy's potential? This is the story of the greatest industrial mobilization in human history, of how democracy proved its superiority over authoritarianism, not on the battlefield, but in the shipyards and factories. A story that began on that fateful Sunday morning at Pearl Harbor, Sunday, December 7th, 1941, 7:48 a.m. Hawaiian time. The first Japanese torpedo bombers dived toward the calm waters of Pearl Harbor. American sailors are still eating breakfast on their decks when the sky erupts with explosions. USS Arizona, the flagship of the Pacific Fleet, detonates after a direct hit from a 1,760-kilogram bomb. The blast is so powerful it is heard 15 kilometers away. 1,177 sailors die instantly. A ship that took 4 years and $13 million to build becomes a blazing tomb in seconds. USS Oklahoma capsizes after 5 torpedo strikes. 429 sailors are trapped inside the overturned hull. Some remain alive for 3 days, pounding on bulkheads in desperate attempts to signal rescuers. In just 2 hours, the Japanese destroyed or seriously damaged 18 American ships. The battleships California, West Virginia, Nevada, all lay burning or sunk in shallow water. 188 American aircraft were reduced to scrap. Fuel depots and ammunition stores continued to explode for hours after the raid ended. But the greatest loss was human. Along with the ships perished thousands of experienced sailors, officers, and technicians, men who knew every detail of the complex systems, who had studied naval tactics for years. They could not be replaced in a matter of months. When the smoke finally cleared, Admiral Kimmel, commander of the Pacific Fleet, stood ashore looking at the ruins of what, that very morning, had been America's mightiest base in the Pacific. "God," he whispered, "what do we do now?" The answer to that question would change history. Dry Dock Number 1, Pearl Harbor. December 8, 1941, 6 a.m. Less than 24 hours after the attack, hundreds of workers are already moving among the smoldering wrecks. They recover bodies, salvage what can be saved, and make the first assessments. Captain Homer Walters, chief engineer of the base, has not slept all night. His notebook is filled with numbers, sketches, calculations. USS Nevada can be saved, he dictates. California too. West Virginia, more difficult, but possible. But Arizona, he stops. Arizona cannot be saved, and yet amid the catastrophe, something remarkable happens. American engineers and workers do not panic. Step by step, methodically, they begin to plan recovery. By noon on December 8th, Walters already has a preliminary plan to rescue 7 heavily damaged ships. In Washington, meanwhile, President Roosevelt convenes an emergency cabinet meeting. Secretary of the Navy, Frank Knox, has just returned from Pearl Harbor. His report is brutal. We have lost more than half of our battle fleet in the Pacific. Japan now has full naval superiority in the region. How long will it take to rebuild the fleet? Roosevelt asks. Knox checks his notes. Experts give estimates ranging from 3 to 5 years. At least 3 years, Mr. President, and that is assuming the Japanese do not strike our shipyards. Roosevelt is silent for 30 long seconds. Then he raises his head. No, not 3 years. 1 year. Give me a new fleet in 1 year. Detroit, Michigan. December 15th, 1941. Henry Ford Jr. stands in the middle of the giant River Rouge plant, staring at the assembly line that only yesterday was turning out Ford automobiles. Today, workers are installing equipment for the production of Pratt & Whitney R-2800 aircraft engines. 30 days, he tells the chief engineer. In 30 days, this plant must produce engines for bombers, not cars, aircraft engines. It seems impossible, but the Ford Motor Company makes the impossible happen. After just 29 days, 1 day ahead of schedule, the first aircraft engine rolls off the line. By the end of 1942, the River Rouge plant will produce 8,685 aircraft engines, more than the entire output of Germany in the same period. But Ford was just one example among thousands. Across America, the fastest industrial transformation in human history was underway. General Motors halted car production and switched to tanks and planes. Chrysler began producing Sherman tanks. Even the Singer Company, famous for sewing machines, started making gun sights for warships. In California, Henry Kaiser, a contractor who before the war built dams and highways, received a contract to construct warships. "I've never built a ship," he admitted frankly to naval officials, "but I know how to organize production." Kaiser applied the same principles of mass production that had made the U.S. auto industry the most powerful in the world. Instead of the traditional keel-to-superstructure method, he introduced modular construction. Huge sections of a ship's hull were built separately in different shops, then welded together on the slipway. The construction time for a Liberty-class transport dropped from a traditional 244 days to an incredible 42. One ship, the SS Robert E. Peary, was completed in a record 4 days, 15 hours and 29 minutes. But the true miracle was not only in speed, but in scale. Before the war, America had 12 major shipyards. By the end of 1942, there were 47. New yards sprang up along the Gulf Coast, the Great Lakes, even inland states along rivers. Amid this chaos of transformation, a new America was born, a nation that learned to think not in months, but weeks, not in years, but months, a nation where the impossible became routine. Richmond, California, Kaiser Shipbuilding, Yard Number 2, January 1942. 23-year-old Wendell Johnson grips a welding torch for the first time in her life. Just 3 months ago, she was a waitress in a small diner. Now she is learning to weld the hulls of warships. "Don't think about being a woman," her instructor, an experienced shipbuilder named McCoy, tells her. "Think about being an American. And Americans build the best ships in the world." Wendell is not alone. Across the yard, hundreds of women are at work. Before the war, fewer than 1,000 women worked in U.S. shipyards. By the end of 1942, that number will exceed 160,000. They become welders, crane operators, mechanics, electricians. They are nicknamed Rosie the Riveters, after a popular song and propaganda poster. But the real women behind the rivet guns were far more diverse than the symbol. Housewives from the Midwest, teachers from the East, farm girls from the South. Many had never even seen the ocean, yet now they were building the ships that would win the greatest naval battles in history. Wilma Briggs, a 34-year-old mother of 3 from Oklahoma, became one of the best crane operators in Richmond. She could swing a 40-ton hull section into place with centimeter precision. "My husband is somewhere fighting in the Pacific," she told reporters. Every ship I helped build might save his life. But women were only part of the mosaic. Kaiser's yards employed African Americans from the South, Mexican Americans from California, immigrants from Europe, people who just months earlier would never have worked side by side because of racial prejudice now stood shoulder to shoulder at welding stations. 16-year-old James Washington from Louisiana ran away from home, lying about his age to get a job at the yard. "My father served in the Navy back in World War I," he said. "He told me ships are our strength. I want to build the strongest ships in the world." By the end of the year, James would become one of the fastest riveters in the yard. His record, 1,247 rivets in a single shift, still stands unbeaten. Richmond Shipyard, number 2. March 1942. Henry Kaiser stands before a giant diagram pinned to his office wall. On it is something the world has never seen before, a fully mechanized process for building warships. Traditional shipbuilders see a ship as a unique work of art, he explains to a group of Detroit engineers. We see a ship as a Ford Model T, standardized, unified, ready for mass production. Kaiser's secret was a revolutionary approach to shipbuilding. Instead of constructing a vessel piece by piece from bow to stern, his team designed a system of 250 standardized sections. Each section was built separately at specialized stations, then welded together in a matter of days. The bow section was made in Shop A, the stern in Shop B, deck sections in Shop C, the engine room in Shop D. Each shop specialized in its part, perfecting the process. When all sections were ready, massive cranes lifted them into place and welded them together on the slipway. The results astonished even Kaiser himself. The SS Robert E. Peary, a 134-meter transport, was completed in just 4 days and 15 hours from first rivet to launch. The Japanese needed 6 months to build a comparable vessel. But the real revolution was not only in speed, but in manpower. A traditional yard employed 2,000 to 3,000 skilled shipwrights. Kaiser's yards ran with 15,000 to 20,000 workers, most of whom had never seen a ship 3 months earlier. Mary Lou Gardner, a 28-year-old teacher from Iowa, became an expert in turbine installation after just 6 weeks of training. "They showed me blueprints, gave me tools, and said, 'Do it,'" she recalled. "I thought I couldn't, but it turned out a turbine is just a big machine, and I've always been good with machines." Tom Miller, a former Kansas farmer, became one of the yard's best crane operators. His record, lowering a 60-ton hull section into place with 5-centimeter accuracy. "On the farm, I drove a tractor," he said. "A crane is just a bigger tractor." By the end of 1942, Kaiser's system was producing 1 Liberty ship every 4 to 5 days. And that was only the beginning. Engineers were already working on even more ambitious projects: destroyers, cruisers, even aircraft carriers. The Newport News Shipbuilding, Virginia. April 1942. Engineer William Francis looks at the empty slipway number 11 and tries to imagine the impossible. Here, on this slipway, in 500 days, the aircraft carrier USS Essex, 270 meters long, 27,000 tons, must appear. Before the war, the fastest carrier construction took 3 years. Now, American shipyards must do it in 16 months. This is madness, Francis thinks. But he already knows that American madness often turns into American genius. The secret behind rapid carrier construction lies in a radical change in design philosophy. Instead of a unique design for each ship, American engineers develop a standardized Essex-class layout. Every carrier of this class is built from the same drawings, with the same systems and the same equipment. Standardization allows component production to start before the design is even finalized. While engineers are refining the ventilation system, workers are already making armor plates. While the fire suppression system is being designed, radar sets are already being produced at other plants. Betsy Coleman, a 25-year-old drafter from Boston, works in the Newport News design office. She and her 12-woman team handle the detailed drawings of the carrier's internal layout. "We work 12 hours a day, 7 days a week," she notes in her diary. "But every drawing we finish today lets the yard start something tomorrow." On the yard itself, an equally astonishing process unfolds. Harry Swenson, an experienced welder from Sweden, leads a crew of 40 newcomers. Most of them were in farming or retail 3 months ago. Now they are welding the most complex parts of a warship's hull. An aircraft carrier isn't just a big ship, Swenson tells his crew. It's a floating airbase with its own power plant, its own airfield, its own city. Every seam you weld must withstand a torpedo or a bomb. Work runs around the clock. 3 8-hour shifts cover all 24 hours. At night, the yard blazes under floodlights, looking from afar like a giant steel mill. Welding sparks throw a fantastic light show, visible for kilometers. By the fall of 1942, 15 carriers of various classes are under construction, simultaneously in American yards. USS Essex, USS Yorktown II, USS Intrepid, USS Hornet II, each born in the flame of welding torches and the thunder of pneumatic hammers. The Japanese build 1 carrier a year. The Americans build 15. But numbers aren't everything. American carriers receive cutting-edge gear, next-generation radar, anti-aircraft mounts, fire control systems. Technologies that existed only in laboratories a year earlier are now being installed en masse aboard ships. Pearl Harbor, Dry Dock Number 1, June 1942. The battleship USS West Virginia slowly rises from the seabed. 6 months earlier, it lay in 12 meters of water, holed by 7 torpedoes and 2 bombs. Now, an armada of pumps is sucking out thousands of tons of water, fuel oil, and sludge. Captain Engineer Robert Hazen stands on West Virginia's deck and can hardly believe his eyes. Inside is a scene of devastation. Buckled bulkheads, machinery reduced to scrap, cables dangling like dead snakes. But the hull is sound. The main turbines can be restored. The ship will live. How long to repair? Admiral Chester Nimitz asks during an inspection. Under normal conditions, 2 years, Hazen replies. But these aren't normal conditions. Give me 8 months. Nimitz nods. In 8 months, West Virginia must return to action, not as a museum piece, but as a fully capable combat unit able to face Japan's newest battleships. The restoration begins at once. Trains from the mainland bring new equipment, radar, anti-aircraft guns, fire control systems, everything the American industry can provide at the cutting edge. West Virginia will receive upgrades that make her stronger than she was before the war. But the true miracle is USS California. She had sunk completely, with only part of her superstructure above water. The Japanese considered her destroyed forever. American engineers thought otherwise. The raising of California took 4 months. Divers worked in total darkness 15 meters down, welding hull breaches from the inside. It was deadly work. At any moment the ship could shift and entomb them under her weight. Jack Thompson, a 23-year-old diver from Texas, spent over 200 hours underwater repairing California. Down there it was pitch black, he recalls. I worked by touch. My hands found the hole. My hands guided the torch. Sometimes I didn't know which way was up, but I knew the work mattered. When California finally surfaced, the bodies of 98 sailors were found inside. They had died instantly on December 7th, but their ship would return to life and avenge them in the battles of 1943. Not every ship could be saved. USS Arizona remained on the bottom as a memorial. USS Oklahoma proved too damaged to restore, but of the 8 battleships hit at Pearl Harbor, 6 returned to service. The Japanese had expected nothing like it. U.S. Naval Observatory, Washington, August 1942. In a classified basement, a team of 40 women mathematicians tackle the war's hardest problem: how to optimize warship production. Grace Hopper, a 35-year-old Yale mathematician, heads the ballistics section, but her real work reaches far beyond that. She builds mathematical models to forecast how much steel, aluminum, and copper each ship type needs, how many labor hours, how much electricity. War is mathematics, she tells her staff. Whoever calculates better wins. The Japanese have experience. We have numbers. Thousands of punched cards, the first computer programs in history, cover the tables. Each card holds data on a single component: weight, dimensions, manufacturing time, required materials. IBM mechanical tabulators process the cards and spit out optimal production schedules. Betty Snyder, a 24-year-old mathematician from Pennsylvania, specializes in logistics. She builds charts showing when and where every component must arrive. If a turbine reaches the yard one day late, the entire build slips a week, she explains. My job is to prevent that. The system these women create lets American shipyards operate with astonishing precision. Every bolt, every rivet is accounted for. Waste is minimized. Downtime is almost nil. Meanwhile, the Japanese rely on traditional planning. Their admirals decide by experience and intuition. American admirals decide using mathematical models that analyze millions of variables. Margaret Hamilton, a young MIT programmer, develops a quality control system for carriers. Her algorithms vet each component before installation. One defective bearing can cripple an entire turbine, she says. Better to find the problem in the lab than in the middle of the Pacific. By the end of 1942, the women's team has optimized production so effectively that U.S. yards are delivering ships 30% faster than originally planned. Japanese commanders cannot understand how the Americans achieve such efficiency. They search for secret technologies, new allies, miracle weapons. But America's true secret weapon is mathematics, and the women who wield it. Doris Day, a 22-year-old from Ohio, calculates optimal armor plate angles for new cruisers. Her work reduces armor weight by 15% while preserving protection, meaning faster ships that can carry more guns. People think pilots and sailors win wars, Doris writes to her mother, but wars are won by those who count better, and we Americans count better than anyone. Atlantic Ocean, 200 miles off New York. September 1942. German submarine U-175, commanded by Captain Heinrich Bruns, stalks American convoys. In the last 6 months, German U-boats have sunk 312 American ships in the Atlantic, more than the losses at Pearl Harbor. America builds ships quickly, Bruns writes in his diary, but we sink them even faster. He does not know that his confidence is premature. In secret laboratories at MIT, a group of young physicists led by Luis Alvarez are developing a revolutionary technology, microwave radar, capable of detecting a submarine on the surface from 50 kilometers away, even in complete darkness. The first prototype is installed on a new kind of vessel, the escort carrier USS Bogue. Built in just 85 days from a converted merchant ship, its mission is to guard convoys and hunt submarines. Captain Giles Short of the Bogue is skeptical of the new equipment. Another toy from the scientists, he thinks. But on September 12, 1942, Bogue's radar detects U-175 at 40 kilometers. The German sub never realizes the danger. A TBF Avenger from the carrier attacks with depth charges. U-175 goes down with all hands. It is the first of many victories for America's new technology against the U-boat menace. But the true revolution takes place in the shipyards. America begins building escort carriers like automobiles, simple, standardized, easy enough that even shipyards with no military experience can learn the process in months. Henry Kaiser and his team designed the Casablanca-class escort carrier, 156 meters long, 19 knot speed, 28 aircraft on board. Most important, a build time of only 6 months from keel laying to completion. The first ship, USS Casablanca, is laid down in January 1942. By July, it is already on its first combat mission. Over the next 3 years, the U.S. will build 50 Casablanca-class carriers, more than all the carriers of every other nation combined. Lieutenant Elizabeth Thompson, one of the first women officers aboard an escort carrier, stands radar watch on USS Card. Every green blip on the screen is a potential submarine, she writes in her log. We are hunting the hunters, and we are finding them. By the end of 1942, German U-boats are losing their grip on the Atlantic. American escort carriers and their radars turn the submarine war from rabbit hunting into a deadly game of cat and mouse, where the Americans are the cats. Pittsburgh, Pennsylvania. Carnegie Steel Mill. October 1942. Blast furnaces roar day and night, turning out armor steel for America's new warships. Inside, the temperature reaches 1,600 degrees Celsius. enough to melt copper. Foreman John Kowalski directs a shift of 500 workers, most of them immigrants from Poland, Ukraine, Italy. Before the war, they made ordinary steel for buildings and cars. Now they are forging the hardest armor steel in the world. Every ton we pour today may save 100 sailors tomorrow, Kowalski tells his crew. No defects, no delays. The problem is not volume, but quality. Armor steel must withstand direct hits from 16-inch shells. That requires a special chemical mix and complex heat treatments. Before the war, only a handful of specialized mills could make it. Now, dozens of plants across America must learn secrets once passed down from master to apprentice over decades. Mary O'Connor, a chemist from Carnegie Mellon, pioneers new methods for testing armor steel. Her lab checks every batch for strength, ductility, corrosion resistance. One bad heat could sink a ship, she warns her assistants, but steel is only half the challenge. Warships also require vast amounts of aluminum for superstructures, radars, and aviation equipment. Before the war, global aluminum production was 600,000 tons a year. The U.S. alone now needs 2 million tons for war needs. Alcoa launches the biggest expansion in its history. New smelters rise in Washington, Oregon, Tennessee, Arkansas, each consuming as much electricity as a major city. At Alcoa's Washington plant works Robert Chang, an American of Chinese descent. Before the war, prejudice left him unemployed. Now he runs an electrolytic cell producing aluminum for carriers. Here they judge me not by my skin, but by my work, he writes to his brother. And I make the best aluminum in the world. The breakthrough comes with new alloys. Alcoa engineers develop an aluminum-magnesium mix 40% lighter than steel, yet nearly as strong. It allows faster ships carrying more weapons. By the end of 1942, U.S. aluminum production has risen five-fold from pre-war levels. Steel output is 300% higher than in 1940. Meanwhile, Japan faces severe shortages of both metals due to Allied blockade. We are losing this war in the blast furnaces, Admiral Isoroku Yamamoto admits in a secret report. America has turned its nation into one giant arsenal. We cannot match their industrial might. MIT Radiation Laboratory, Cambridge, Massachusetts. November 1942. Professor Luis Alvarez stands before a refrigerator-sized secret device. It is a magnetron, the heart of a new radar system that will change the naval war. This can detect a Japanese ship at 100 kilometers in any weather, Alvarez explains to Navy engineers, at night, in fog, in storms. The Japanese will never approach unseen again. The magnetron was invented in Britain, but Americans refine it with astonishing speed. Before the war, radars ran on kilowatts. The new American magnetron generates megawatts, 1,000 times more power. At Raytheon's secret Boston plant, 24-year-old physicist Pearl Cornell oversees magnetron production. Every magnetron we build gives a ship eyes that see through night, she tells her team. The work requires extreme precision. Resonator cavities must be machined to thousandths of a millimeter. One flaw and the unit fails. Before the war, magnetrons were hand-built in labs. Now they must be mass-produced by the thousands. Here, American genius for mass production strikes again. General Electric engineers design special machines to craft resonators with laboratory precision. Women workers master these machines in weeks. The first ship equipped with the new radar is the cruiser USS Cleveland. In December 1942, she trials off California. The results amaze even her designers. The radar spots a destroyer 85 kilometers away, 4 times farther than any pre-war system. But radar is only part of the technological surge. Bell Labs is building new long-range communication systems. General Electric is developing more powerful, more reliable turbines. Dr. Vannevar Bush, head of the Office of Scientific Research and Development, coordinates 30,000 scientists nationwide. This war will be won in the laboratories, he tells a White House meeting. Whoever invents first wins. Japan, meanwhile, relies on proven technologies and veteran crews. Their ships are well built, their sailors well trained, but they lack the resources and the scientific base for a technological revolution. By the end of 1942, the difference is clear. American ships with radar can fire accurately in total darkness. Japanese ships still depend on lookouts and navigators' instincts. Pearl Harbor, Pacific Fleet Headquarters, December the 7th, 1942, exactly 1 year after the Japanese attack. Admiral Chester Nimitz stands in the very spot where, a year earlier, he had watched the burning wreckage of the U.S. fleet. Now, the view before him is entirely different. In the harbor lie 47 warships, more than before the attack. Among them are 4 new carriers, 8 cruisers, 20 destroyers. USS West Virginia and USS California, raised from the bottom, have been fully modernized and are now more powerful than any Japanese battleship. A year ago, the Japanese thought they had destroyed the American fleet, Nimitz tells his staff. They were wrong. They only woke it up. The numbers are staggering. On December 7, 1941, the Pacific Fleet counted 9 battleships, 3 carriers, 24 cruisers, 80 destroyers. On December 7, 1942, 12 battleships, 8 carriers, 35 cruisers, 150 destroyers. And that is just in the Pacific. Nationwide, the U.S. Navy has grown from 790 ships to 2,100 ships in a single year. The fastest naval expansion in history. But numbers don't tell the full story. The new American ships are not just more numerous, they are technologically superior. Every new carrier carries radar systems the Japanese have not even invented. Every cruiser is armed with next-generation anti-aircraft guns. Every destroyer has sonar able to track a submarine at 200 meters. In Tokyo, Admiral Isoroku Yamamoto studies intelligence reports on the U.S. fleet. The numbers seem impossible. This cannot be true, he tells his aide. Humanity is not capable of building ships so quickly. But the intelligence is correct. The U.S. is producing 1 Liberty ship every 4 days, 1 escort carrier every 6 months, 1 cruiser every 8 months, 1 battleship every 14 months. We did not underestimate their weapons, Yamamoto writes in his diary. We underestimated their industrial power. This is not the America we knew before the war. This is something else entirely. He is right. In a single year, America has transformed from an isolationist nation into the most powerful war machine in history. 12 million Americans now work in defense industries. 6 million women have stepped into jobs once held by men gone to war. The result of this transformation will become clear in 1943, when American carriers go on the offensive across the Pacific. But the foundation of victory has already been laid, in the factories of Detroit, in the shipyards of California, in the laboratories of MIT, Tokyo, Imperial General Headquarters. January 1943, Admiral Osami Nagano, Chief of the Naval General Staff, holds in his hands an issue of Life magazine with photos of new American ships. On the cover, the carrier USS Essex sliding down the ways. Date: July 25, 1942. Impossible, Nagano repeats for the 4th time in an hour. By our calculations, the Americans could not rebuild their fleet before 1945, but they are doing it now. Captain Minoru Genda, one of the planners of Pearl Harbor, studies reconnaissance photos of American shipyards. They show yards working around the clock, dozens of ships under construction at once. We destroyed their ships, he says, but we did not destroy their ability to build new ones. Japanese intelligence struggles to explain America's success. Agents report strange things. Women working as welders, farmers building carriers, teenagers operating cranes. The entire American nation has become one giant factory, one spy in San Francisco writes. But the greatest shock is the quality of American ships. The Japanese expected hastily built vessels to be unreliable, poorly armed, weakly armored. Instead, the new U.S. fleet is technologically ahead of their own. Rear Admiral Ryunosuke Kusaka, a naval technology expert, examines captured U.S. radar equipment. Their sets are 10 times more powerful than ours, he reports. They can fire accurately in complete darkness at 20 kilometers. Japanese engineers attempt to copy U.S. technology, but hit a wall. Japan lacks the industrial base for mass production of advanced electronics. The U.S. produces thousands of magnetrons per month. Japan can make only dozens. We fought a country we did not know, Yamamoto writes in his diary. We thought America was a nation of merchants and farmers. It turned out to be a nation of engineers and inventors. The greatest shock for Japanese commanders is America's speed of adaptation. Japan planned war on the basis of experience and tradition. The US turned war into an industrial process, victory going to whoever learned faster and produced more. February 1943. Japanese submarine Ijai-19 attacks an American convoy off Guadalcanal. Its captain expects an easy kill. Instead, he faces a coordinated counterattack from 3 escort carriers with radar and anti-submarine aircraft. I-19 goes down in minutes, a symbolic moment. The U-boat hunters of yesterday are now the hunted. Detroit, Michigan, Fort Willow Run Plant, March 1943. Rosie Wilson, 62-year-old grandmother of 5, ends her shift on the B-24 bomber line. In 8 months, she has learned to operate precision machines, read technical drawings, and assemble some of the most complex aircraft components of the war. My grandkids think I'm a hero, she laughs, peeling off her overalls. But the real heroes are all of us. Every woman, every man, every teenager working for victory. She is right. America's industrial miracle was not created by generals or politicians. It was built by millions of ordinary people who chose to attempt the impossible. Thomas Harrison, a 17-year-old from Alabama, runs a 50-ton crane in Mobile Shipyard with the precision of a surgeon, lifting hull sections into place. Before the war, I'd never even seen the sea, he says. Now, I'm building the ships that will defeat Japan. Maria Gonzalez, a 25-year-old Mexican-American from California, becomes one of the best inspectors at Douglas Aircraft. She checks every part destined for the Pacific Front. Any mistake I miss could cost a pilot his life, she says. I can't let that happen. David Cohen, a German-Jewish refugee, works as an engineer at the Brooklyn Navy Yard. Driven from his homeland by the Nazis, he now designs ships to fight Hitler. This is the best revenge, he tells his colleagues. Every ship I help design brings us closer to Nazi defeat. But the true heroes are the women. Before the war, they made up 12% of the U.S. workforce. By 1943, the figure is 36%. They became pilots ferrying warplanes, engineers designing tanks, welders building ships. Norma Jean Baker, future Marilyn Monroe, works at Radioplane Munitions, assembling drones for gunnery training. Peggy Carter leads an engine assembly crew at Pratt & Whitney. Grace Kelly, future Princess of Monaco, models for propaganda posters urging women to the factories. By war's end, American women will have built 86,000 tanks, 296,000 aircraft, 15,000 ships. They will have turned the U.S. into the arsenal of democracy, as President Roosevelt called it. Most important of all, they proved that democracy could mobilize faster and more effectively than any dictatorship. Hitler and Japan's militarists thought democracy weak, incapable of sacrifice and decisive action. They were wrong. Pacific Ocean, 600 miles northwest of Guadalcanal, June 1943. The Japanese carrier Hio tries to flee from an American strike group. On the horizon loom the silhouettes of 5 U.S. carriers: USS Essex, USS Yorktown, USS Lexington, USS Bunker Hill, USS Enterprise. A year earlier, only one of these existed. Admiral Jisaburo Ozawa, commander of the Japanese force, stares through his binoculars at the American armada, unable to believe his eyes. Where did they get so many ships? He asks his navigator. There is no answer. The U.S. fleet has grown so quickly that Japanese intelligence cannot keep up. The battle that begins symbolizes a new reality in the Pacific. The Japanese have experience, tradition, superbly trained crews. The Americans have a 5-to-1 numerical advantage and a technological edge that cannot be overcome. American carriers launch 300 aircraft at once. The Japanese can send 60 to meet them. U.S. radars detect incoming Japanese planes at 100 kilometers, giving ample time to prepare defenses. Japanese pilots fly blind, relying only on navigation skills. Hio goes to the bottom at 1532. With her die 1,200 Japanese sailors and 40 veteran pilots. The Americans lose 12 aircraft and 29 men. The mathematics of war has turned mercilessly against Japan. This battle is only one episode in a grand strategy born on the factory floors of 1942. The U.S. fleet is now so powerful it can fight in two oceans at once, half the ships against Japan in the Pacific, the other half against Germany in the Atlantic. By the end of 1943, the Americans will have 24 carriers in service. Japan will have 4. The U.S. will launch 1 new carrier every 2 months. Japan will complete no new carriers before 1944. But the true significance of America's industrial miracle goes far beyond tallies of ships and planes. It changed the nature of war itself. Traditional factors, commanders' experience, soldiers' courage, geographic advantages moved to the background. What mattered most was a nation's capacity to mobilize its industrial resources. We did not lose the war at Midway, Japanese historian Senshukai Abe would later write. We lost it in American shipyards in 1942. When the Americans learned to build ships faster than we could sink them, our defeat became inevitable. The Industrial Revolution of 1942 set a precedent that would shape history for decades. Nations learned that in modern war, victory belongs not to the side with the best generals, but to the side with the strongest industry. This lesson would not be forgotten in Moscow, Beijing, or Washington. The Cold War would become a contest of industrial potential, the space race, a struggle of technologies. Future conflicts would bear the imprint of America's 1942 experience. Pearl Harbor, USS Arizona, Memorial. December 7th, 2041, 100 years after the attack. An old man lays flowers at the shrine and recalls his grandfather's stories of those distant days when America turned from victim to victor in a single year. What remains of that incredible year? What can we learn from the people who made the impossible possible? First lesson, unity. When a nation rallies around a common purpose, it can work miracles. In 1942, Americans set aside racial prejudice, gender stereotypes, class divides. They worked together for a shared future, and that made them unbeatable. Second lesson, innovation. Americans didn't just build more ships, they invented new ways to build them. They applied mass production to unique, complex products, blending traditional crafts with cutting-edge technology. A revolution in shipbuilding became part of a broader technological revolution. Third lesson, the role of women. The year 1942 forever changed what society believed women could do. Rosie the Riveter became a symbol not only of the war effort, but of emancipation. Women who learned to build ships did not want to return to old roles after the war. They became engineers, doctors, scientists, politicians. Fourth lesson, democracy. Dictators assumed democracies were weak because they debated and compromised. America's 1942 experience proved the opposite. When democracy mobilizes, it becomes the most effective form of organization. People who work by choice will always outperform those forced to obey. Fifth lesson, the speed of change. What seemed impossible in December 1941 was reality by December 1942. 1 year was enough to tilt the global balance of power. In our era, change moves even faster. Countries, companies, and people who cannot adapt are doomed to lose. But the deepest lesson is about the human spirit. The Americans of 1942 were not superhuman. They were ordinary people in extraordinary circumstances. They did not give up. They did not despair. They rolled up their sleeves and went to work. Wendell Johnson, a welder at Kaiser's Yard, lived to be 95. In her memoir, she wrote, "People often ask how we managed to do the impossible. The answer is simple. We didn't know it was impossible, and by the time we found out, it was too late to stop." Perhaps that is the secret of America's 1942 miracle. Sometimes the greatest achievements are born not from a confidence, but from a refusal to surrender. Not from knowing what is possible, but from refusing to accept what is impossible. The furnaces of American shipyards have long since gone cold, but their fire still lights the way for all who believe in the power of the human spirit and are willing to work for a better future. On December 7th, 1941, the Japanese thought they had destroyed the American dream. In truth, they awakened American genius, and the world would never be the same. Are we capable of such miracles today? The question remains open. But the story of 1942 reminds us, when humanity unites behind a common goal, the impossible becomes inevitable. Japanese Sergeant Hiroshi Tanaka lies in his trench, clutching his Arisaka Type 99 rifle. The air is cut by the familiar whistle of a mortar. The Americans are attacking again. But this time, something is different. Instead of a deafening explosion and metal fragments flying everywhere, the island is wrapped in a thick white fog. Tanaka stares into that cloud, slowly spreading between the trees. Where is the explosion? Where are the shrapnel fragments? Why aren't his comrades screaming in pain? Instead, an odd silence reigns, broken only by muffled American voices approaching through the impenetrable smoke screen. Within seconds, the sergeant understood the terrible truth. The Japanese were losing this war not only because of American equipment or numbers. They were losing because the Americans fought in a completely different way. They used weapons not for destruction, but for concealment. When we talk about the Second World War in the Pacific, we usually recall aircraft carriers, kamikaze, atomic bombs. But there is a lesser-known story about how the American Army revolutionized the use of mortars, forcing Japanese commanders to rewrite tactical doctrine. In 1941, American mortars were pretty standard, heavy tubes that fired high explosive rounds. The Japanese understood this. Their own mortars, the Type 89 and Type 97, worked on the same principle. It hits, it explodes, it destroys. Simple wartime logic. But by 1943, something had changed drastically. Japanese military reports began to fill with mentions of an American smoke fog, mysterious clouds, and hidden attacks. At first, headquarters chalked this up to nervousness among soldiers. Later, it became clear the Americans were really fighting differently. This is a story about how tactical innovations can matter more than technological superiority, about how the use of smoke rounds became one of the key factors in American victories on the Pacific Islands, and about why Japanese generals never fully adapted to the new American tactics. It all began in September 1942 on Guadalcanal, when Lieutenant Colonel James Murphy of the 1st Battalion, 164th Infantry Regiment, faced a problem. His unit had to attack Japanese positions near Henderson Field, but the open ground left no chance for surprise. Murphy was an experienced officer who had also served in World War I. He remembered how the British used smokescreens during the Battle of the Somme in 1916, but then smoke was made by special smoke grenades carried by infantry. That was awkward and dangerous. What if we fired smoke from mortars? The lieutenant colonel thought, eyeing his 81mm M1 mortars. The battalion had 8 of those, and each could fire up to 20 rounds per minute. The problem was, there were few smoke rounds in the standard ammunition load. At the time, American doctrine envisioned using smoke rounds only to mark targets or for artillery fire correction. No one thought to use them en masse to conceal infantry. Murphy was lucky. A transport had just arrived at Guadalcanal with extra supplies, among them about 200 M57 smoke rounds. The lieutenant colonel made a decision, later called revolutionary, to use all the smoke rounds at once to create a continuous screen. On September 14, 1942, at 0630, 8 American mortars began a methodical barrage on the Japanese positions. But instead of ordinary high explosive fire, the air filled with thick white smoke from the M57 phosphorus rounds. Within 5 minutes, the area around the Japanese trenches turned into an impenetrable cloud. Visibility dropped to 2 or 3 meters. Then the American infantry attacked. Captain Keiji Sato of the 2nd Company, 228th Infantry Regiment, commanded the defenses near the airfield. When the American barrage began, he ordered his men to take cover in their trenches and prepare to repel an attack after the bombardment ended. But the bombardment was odd. Instead of deafening detonations, there were only muffled pops. The ground did not shake with explosions. No shrapnel whistled through the air. Instead, the air gradually filled with a thick white fog with a distinct chemical smell. A gas attack, Sato thought at first. The Japanese army had experience with chemical warfare in China and knew American capabilities in this area. The men hastily put on gas masks, bracing for the worst. But there was no gas. The fog proved to be ordinary smoke, though unusually dense and persistent. Sato relaxed. The Americans were trying to confuse Japanese observers before the main attack. Soon, however, the captain heard voices. American voices. Very close. Right in the center of the smoke screen. That was impossible. No sensible commander sends infantry to attack blindly, especially over the marshy terrain of Guadalcanal. Sato ordered fire into the sound. Japanese machine guns, the Type 96 and Type 99, opened up with a spray of lead into the smoke cloud. But the Americans did not retreat. On the contrary, their voices grew nearer and more numerous. Suddenly, a figure in American uniform appeared from the mist, just 10 meters from the Japanese trench. Then another and another. American soldiers moved slowly, carefully but confidently, using the smoke as perfect cover. Hand-to-hand fighting began. The Japanese had the advantage of knowing the ground, but the Americans used smoke as an ally. They emerged from unexpected directions, struck, and dissolved back into the white haze. After 1 hour of fighting, Captain Sato's company ceased to exist. Not due to artillery or air power, but from a standard infantry attack conducted under the cover of smoke rounds. It was a lesson Japanese command should have learned, but did not. Lieutenant Colonel Murphy could not believe the results of his experiment. His battalion seized well-fortified Japanese positions, suffering only 7 killed and 23 wounded. By Pacific War standards, where every trench had to be taken at great cost, this was simply incredible. But the most important thing was something else. The Americans had discovered a fundamentally new way of fighting. Smoke rounds turned mortars from an artillery weapon into a tactical tool for infantry support. This changed the whole philosophy of assault operations. Traditional tactics called for a powerful artillery preparation to destroy or demoralize the enemy, then infantry would assault the weakened positions. The problem was that preparatory bombardment warned the enemy of an upcoming attack and gave them time to get ready. Smoke rounds offered a fundamentally different approach. Instead of destroying the enemy, the Americans blinded them. The Japanese remained alive and combat capable, but could not effectively use their firepower. This allowed infantry to close in and exploit advantages in close combat. Additionally, smoke screens had a psychological effect on Japanese soldiers. They did not know from where to expect the attack, how many Americans were approaching, or whether they were already encircled. Uncertainty turned out to be more powerful than artillery fire. Murphy detailed his experience in a report to the 15th Corps staff. He emphasized 3 key advantages of the new tactic: surprise of the attack, the psychological effect on the enemy, and significantly reduced friendly casualties. The report reached General Alexander Patch, commander of the 14th Corps, and later the staff of Admiral Chester Nimitz. Everyone understood. The Americans had found a new way to fight Japan's fight-to-the-last-man tactics. By October 1942, mass rearming of American mortar units with smoke rounds began. Where previously a battalion carried 10 to 15% smoke rounds of its total ammunition, that figure rose to 40 to 50%. At the same time, intensive training began. American soldiers learned to operate in limited visibility, coordinate actions blind, and use sound signals instead of visual cues. It was a real revolution in infantry tactics. When reports of the American smoke fog began to reach the 17th Army headquarters at Rabaul, Lieutenant General Harukichi Hyakutake at first did not believe them. His combat experience in China and Manchuria told him that smoke screens were an auxiliary measure, not a primary tactic. Perhaps these are isolated incidents, the general thought as he read reports from different sectors. But by November 1942, it became clear the Americans were systematically using the new tactic across multiple fronts. Most striking was the battle for Kokoda on the 19th of November, 1942. The Japanese 229th Infantry Regiment under Colonel Shoichi Yokoyama held well-prepared positions on the hills along the river. The colonel was confident that the Americans would need several days to storm those heights, but the Americans chose a different approach. At 1400 hours, 24 81mm mortars from the 1st Battalion, 27th Infantry Regiment began a methodical bombardment of the Japanese positions with M57 and the new M64 smoke rounds. Visibility along the entire defensive line fell to only a few meters. Colonel Yokoyama ordered blind fire, but it proved futile. American troops advanced in short dashes, using natural folds of terrain and the dense smoke. Japanese machine gunners fired into empty air, rapidly expending ammunition. Worst of all, the Japanese could not call in effective artillery support. Their forward observers could see nothing through the smokescreen and could not correct fire. The Americans had effectively denied Japanese artillery the ability to intervene in the fight. Within 2 hours, American infantry had broken through the key heights. Colonel Yokoyama was forced to withdraw, leaving more than 300 men on the field. It was not a classical encirclement or rout. The Japanese were simply unable to fight effectively under conditions the Americans created. Hyakutake grasped the seriousness of the problem and ordered urgent development of countermeasures. Japanese engineers began experimenting with their own smoke rounds, hoping to disperse the American fog. But their mindset was fundamentally different. The Japanese treated smoke as an obstacle to be overcome. The Americans had turned it into an instrument of attack. That difference in approach proved critical for subsequent island battles. By the end of 1942, Japanese command issued special instructions on countering American smoke attacks. Recommendations included using grenades to clear the fog, setting up extra observation posts, and keeping reserve forces ready for counterattacks. But these measures were reactive rather than proactive. The Japanese tried to adapt to the American tactic instead of developing their own alternative. That became one reason for their later defeats. The success of smoke tactics on Guadalcanal drew the attention of American military engineers. The primary development center was the Aberdeen Proving Ground in Maryland, where a team led by Lieutenant Colonel Robert G. Ball worked on improvements. Ball realized that standard M57 smoke rounds, developed in the 1930s, did not fully meet the new tactical requirements. They produced dense smoke, but it dispersed quickly in Pacific tropical winds. A round was needed that would create a more persistent screen. The first breakthrough came in December 1942, when Ball's team developed the improved M64 round. The main difference was a new smoke mixture. Instead of relying solely on white phosphorus, they used a combination of phosphorus with zinc powder and organic additives. The new mixture produced about 40% more smoke that stayed aloft far longer. If the M57 created a screen lasting 8 to 12 minutes, the M64 provided cover for 15 to 20 minutes, even in moderate wind. That allowed American infantry to execute more complex maneuvers. But the most important innovation was the M83, developed in February 1943. Unlike earlier models, this round produced gray smoke with a faint yellowish tint. The chemical mix imitated natural fog, making the smokescreen less noticeable to Japanese observers. Additionally, the M83 had an extended duration, up to 25 to 30 minutes. Americans could create large-scale smokescreens that covered several square kilometers and persisted for the duration of an operation. At the same time, new employment tactics were developed. Instead of a single-mass barrage, Americans began using cascading smoke. The first screen covered the initial assault. 15 to 20 minutes later, as the smoke began to thin, a second wave of rounds would sustain the advance. This pattern could continue for hours. Japanese intelligence tried to obtain samples of the new American rounds, but this proved difficult. Smoke mines, unlike high explosive shells, largely burned away on detonation and left few sizable fragments. Japanese chemists had a hard time deciphering the composition of the new smoke mixture. When they finally analyzed fragments of an M64 captured on New Guinea in March 1943, the Japanese were astonished by the complexity of American technology. Their own Type 94 smoke rounds seemed primitive in comparison. The attempt to create a Japanese analog to the M64 took 6 months and produced unsatisfactory results. Japan's industry lacked certain chemical reagents and precise dosing technology. Moreover, command did not grant the development of smoke munitions a high priority. The real proving ground for smoke tactics became the New Guinea campaign of 1943. General Douglas MacArthur, commanding the Southwest Pacific Theater, took a personal interest in new capabilities of American mortars. MacArthur understood that New Guinea's jungle was ideal for smoke tactics. Dense vegetation naturally limited visibility, and additional smokescreens made Japanese orientation practically impossible. The humid tropical climate also helped retain smoke in the air. The The first large-scale operation took place on the 30th of January 1943 during the landing at Nassau Bay. Colonel Alexander Mack's 41st Infantry Regiment was tasked with seizing a Japanese airfield defended by 1,200 men under Major Kimura Heizo. Mack devised a complex plan codenamed Gray Morning. The operation began at 0530 with a massive smoke barrage from 36 81mm mortars. Within 20 minutes, the entire area around the airfield had turned into a solid gray cloud. But Mack did more than simply lay down smoke. During the preparatory fires, some mortars continued to fire M64 smoke rounds while others switched to high explosive mines, creating an auditory illusion of a large-scale attack from the south. Meanwhile, the regiment's main forces landed by assault boats on the north shore, using the smokescreen as cover. Major Kimura believed the demonstration and shifted most of his forces to repel the main attack from the south. By the time he realized his mistake, American troops had secured the northern part of the airfield and emplaced their own mortars. The most interesting element of the operation was the use of mobile smoke. American engineer units mounted special M1 smoke generators powered by diesel on Willys MB Jeeps. These vehicles moved ahead of infantry, producing a moving smoke screen. The Japanese had never seen such tactics. Soldiers spoke of American ghosts appearing and vanishing in the gray mist. The psychological effect proved as important as the tactical advantage. After 6 hours of fighting, the Americans captured the airfield, losing only 19 killed. Japanese casualties exceeded 800. The 1-to-40 loss ratio was record-setting even for the Pacific War. The success of Operation Gray Morning convinced American command of the effectiveness of smoke tactics. By summer 1943, all infantry divisions in the Pacific had increased stocks of smoke rounds and special equipment for creating mobile screens. The Japanese tried to adapt by developing fire zones. The idea was to pre-sight likely approaches and fire blindly when smoke screens appeared. But this rapidly consumed ammunition without guaranteed results. By early 1944, American smoke tactics had reached perfection. Operation Flintlock, the capture of Kwajalein Atoll in the Marshall Islands, became their culmination. Admiral Raymond Spruance, commanding the Fifth Fleet, had the most powerful force ever assembled for an amphibious operation. But the main weapon was not battleships or carriers. It was 240 mortars of various calibers with enormous stocks of smoke shells. Kwajalein was defended by about 8,000 Japanese troops under Rear Admiral Monzo Akiyama, an experienced officer. Akiyama had studied American smoke tactics from reports of Guadalcanal and New Guinea. He prepared special countermeasures. The Japanese placed dozens of searchlights to disperse the American fog. They set up extra observation posts in tall palms. They created a system of alternate firing positions for combat in limited visibility. Akiyama was convinced he could neutralize the American smoke advantage. On the 31st of January, 1944, at 0900 hours, began the heaviest smoke barrage in the history of the Pacific War. In the first hour, American mortars fired more than 3,000 smoke rounds of various types. The entire atoll disappeared under a gray cloud. But the Americans had prepared a surprise. Instead of a simple attack under cover of smoke, they used a new tactic: multi-layered screening. First came a base screen 10 to 15 meters above ground. Then, low smoke rounds burst right over the water. Finally, high rounds created a canopy at 30 to 40 meters altitude. The result was overwhelming. Japanese searchlights lit up nothing but a solid wall of gray. Observers in palms saw nothing through the upper layer. Even air spotters could not identify the American landing zones. Meanwhile, U.S. landing craft approached the shore under complete cover. The Japanese heard engine noises but could not gauge the number of vessels or the main direction of attack. Admiral Akiyama was forced to spread his forces along the whole perimeter, not knowing where the blow would fall. At 11:30, the landings began. The Americans used another innovation: differentiated screening. At the main landing zones, the smoke was thinner, allowing Marines to orient quickly. At demonstration zones, the smoke was densest, simulating large-scale operations. Within 2 hours, the Americans had secured beachheads at 4 points on the atoll. The Japanese, disoriented by the smoke screens, could not organize effective counterattacks. Kwajalein fell in 4 days instead of the expected 2 weeks. Colonel Takeshi Sugihara, one of the few Japanese officers to survive the American smoke attacks on Saipan, left detailed memoirs about the psychological impact of the new tactics. His writings reveal how deeply the smoke screens undermine Japanese morale. "The worst thing is not that you can't see the enemy," Sugihara wrote. "The worst thing is not knowing if he can see you. The Americans move through the smoke as if they have special eyes. They know where you are, but you know nothing of them." This captured the general feeling of Japanese soldiers. American infantry truly had advantages in low visibility conditions. First, they created the smoke screens themselves and knew their layout. Second, they developed special sound-based orientation systems and carefully reconnoitered terrain in advance. Most important was psychological preparation. American soldiers trained under zero visibility conditions at special ranges in California and Texas. They grew used to disorientation and learned to overcome the instinctive fear of the unknown. The Japanese, by contrast, regarded smoke as a hostile element. Their military culture emphasized visual contact with the enemy. The samurai code of Bushido spoke of looking death in the eye, but what to do when no eyes could be seen? Smoke attacks especially crippled Japanese snipers. Traditionally, some of the most effective imperial troops, Japanese snipers, were masters of camouflage, optics, and marksmanship, but smoke stripped them of their main strength: long-range fire. Americans deliberately used smoke to neutralize sniper nests. Even if a sniper survived, he could not fire effectively through dense fog. This demoralized Japan's elite. The impact on Japanese officers was no less serious. A commander who cannot see the battlefield loses control. Japanese tactics emphasize personal leadership from the front, but smoke screens made this impossible. Colonel Sugihara described one episode on Saipan when he lost contact with his regiment for 3 hours because of smoke. "I knew my soldiers were somewhere near, I heard their voices, but I could give no orders. The Americans had turned me into a deaf-mute commander." Japanese attempts to adapt often bordered on tragicomedy. On Guam, soldiers began carrying bells to identify friend or foe in smoke. Americans quickly learned the trick and used captured bells for deception. On Leyte, Japanese troops tried to blow away American smoke with aircraft propellers salvaged from wrecks. The idea was clever, but the execution disastrous. The propellers made so much noise that Americans easily located and destroyed them with artillery. By mid-1944, Japanese command finally realized that American smoke tactics were not a temporary gimmick, but a long-term strategic advantage. The Imperial General Staff assigned Captain Hiroshi Nakamura of the 6th Army's Technical Branch to develop effective countermeasures. Nakamura was a brilliant engineer, graduate of Tokyo Technical University and trained in Germany. He understood that Japan was losing the technological race not from lack of knowledge, but from neglect of secondary weapons. The first Japanese developments were crude. Type 99, Kiri, fog. Shells were meant to disperse American screens with explosive blasts. The idea was that blast waves would blow smoke away. In practice, it failed. The smoke quickly reformed, wasting ammunition. More successful was the Type 100 Akari, light, illumination round. It used a magnesium charge that burned for 2 to 3 minutes, theoretically letting the Japanese see through smoke. Its first combat use was at Saipan on the 15th of June, 1944. The results were mixed. The Japanese did glimpse U.S. positions during a night attack, but the bright light also exposed themselves, making them easy targets for American snipers. The Americans adapted quickly. They introduced special M76 rounds with a dual smoke mix, the first layer a normal white, the second a dark gray that absorbed light. Japanese illumination rounds became useless. The most interesting Japanese design was the Type 101 Kase, wind shell. Nakamura reasoned that the best way to fight smoke was mechanical dispersal. The shell carried a small electric-powered fan that activated on landing. In theory, it was sound. A strong fan could clear a smoke screen in minutes. In practice, Japanese industry could not produce reliable compact motors. Most Kase shells simply broke on impact before activating. Those that did work ran less than a minute due to faulty electronics. U.S. troops easily destroyed them with grenades or small arms fire. Japan's final attempt was to develop its own smoke rounds for counter screens. The idea was to overlay American smoke with Japanese smoke, forcing both sides to fight equally blind. Type 100. 2. Kirikeishi, return fog. Shells did produce thick smoke, but Japan's chemical industry could not match US quality. Japanese smoke was less persistent, dispersed faster, and had a yellowish tint, making it easy to recognize. Moreover, Japan lacked enough mortars for large-scale smoke use. Most artillery was focused on high explosive and armor-piercing ammunition. Rearming for smoke shells would have required a radical logistics overhaul, something for which Japan had neither time nor resources. The battle for Iwo Jima in February to March 1945 became the clearest demonstration of the perfection of American smoke tactics. Lieutenant General Tadamichi Kuribayashi, who commanded the island's Japanese defenses, was considered one of the Imperial Army's finest tacticians. Kuribayashi studied American methods in detail and prepared the ideal defense against smoke attacks. The Japanese built a system of underground tunnels that allowed forces to be shifted regardless of surface conditions. They installed camouflaged observation posts with armored glass viewports. They prepared pre-registered fire zones for blind fire. On the 19th of February, 1945, the landings of the U.S. 3rd, 4th, and 5th Marine Divisions began. The Americans employed the most complex smoke tactic of the entire war: adaptive multi-phase screening. The operation opened with a false screen, dense smoke over the northern part of the island, where the Americans feigned preparations to land. The Japanese shifted forces there, but the real assault hit the southern beaches under a transparent smoke. A new type of screen that limited visibility to 50 to 100 meters without fully blocking it. Kuribayashi quickly grasped the deception and tried to redeploy. But the Americans launched the second phase: deep screening. Smoke rounds began falling not only along the front line, but also deep in the Japanese defense, blocking the movement of reserves. The most intricate element was the third phase: selective screening. American observers working from naval vessels precisely identified Japanese firing points and blanketed them with individual smoke screens. Japanese machine gunners and artillery crews remained alive, but could not deliver aimed fire. General Kuribayashi tried to use the underground tunnels to bypass the screens, but the Americans had anticipated this as well. Special penetrating M89 rounds were developed specifically for Iwo Jima. They detonated with a delay, allowing smoke to seep into underground structures. Especially effective was the use of mobile smoke generators mounted on Sherman tanks. These vehicles moved ahead of the infantry, producing a moving screen while providing fire support. The Japanese could not effectively counter these smoke tanks. Over 36 days of fighting, the Americans lost about 7,000 killed, enormous by Pacific War standards. Yet, without smoke tactics, losses could have been many times higher. The Japanese defense of Iwo Jima was so formidable that only smoke screens allowed the Americans to close with enemy positions. In his final radio message on the 26th of March, 1945, General Kuribayashi wrote, "The Americans have turned our island into a gray world where one cannot fight in the samurai way. They have deprived us of the chance to look the enemy in the eyes before death." This line symbolically reflected the collapse of traditional Japanese military philosophy in the face of American technological innovation. The battle for Okinawa was the last major operation in which the Americans used smoke tactics on a mass scale. Lieutenant General Mitsuru Ushijima, commander of the Japanese 32nd Army, made a final desperate attempt to find an effective answer to American smoke dominance. Ushijima was one of Japan's most experienced commanders. He had served in China, studied European lessons from World War I, and understood the tactical value of smoke screens. Preparations for Okinawa's defense lasted nearly a year. The Japanese created the most complex defensive system of the entire Pacific War. Unlike other islands, where defenders tried to throw the enemy back at the beaches, Ushijima decided to lure the Americans inland and destroy them in pre-prepared positions. The central innovation was a system of anti-smoke bunkers. Japanese engineers built structures with special ventilation designed to blow out smoke. The bunkers had airtight doors, air filters, and autonomous life support systems. On the 1st of April, 1945, Operation Iceberg, the American invasion of Okinawa, began. General Simon Buckner's 10th Army had a record stockpile of smoke munitions, over 200,000 rounds of various types. The Americans started with traditional mass screening, but quickly realized the Japanese had prepared. The anti-smoke bunkers actually worked. Japanese machine gunners and artillerymen continued to fire effectively even through thick screens. General Buckner was forced to adapt. The Americans began using point screening. Instead of continuous curtains, localized smoke pockets were laid around specific Japanese positions. This demanded much greater precision, but yielded better results. The most effective combination proved to be smoke screens with flamethrower assaults. American flamethrower teams approached bunkers under cover of smoke and then destroyed the ventilation systems with direct hits. After that, the anti-smoke structures became ordinary traps for their defenders. Ushijima tried one last gambit: mass counterattacks timed for the moments when American smoke began to dissipate. The idea was to strike as visibility returned before the Americans had fully reoriented. This tactic worked a few times in April 1945, inflicting tangible losses on the Americans. But the Japanese lacked reserves to employ it systematically. Each counterattack cost hundreds of irreplaceable soldiers. By May 1945, it was clear Japanese resistance on Okinawa was doomed. American smoke tactics again proved effective, though not as decisive as on previous islands. The Japanese learned to partially counter the screens, but never fully neutralize them. On the 21st of June, 1945, General Ushijima committed seppuku in his command bunker as American troops, under cover of smoke screens, closed on the last defensive line. His final order included a line, "The enemy fights not with the sword, but with the fog. We did not learn to fight ghosts." After the war, American and Japanese military historians conducted a detailed analysis of smoke tactics in the Pacific Campaign. The results were striking. Smoke rounds changed the character of the war, no less than radar or jet aircraft. Colonel James Murphy, the same officer who first employed mass screening on Guadalcanal, headed a post-war commission assessing the new tactics' effectiveness. The statistics were impressive. In operations using smokescreens, American casualties were on average 60 to 70% lower than in traditional assaults. The most important conclusion was the realization that smoke rounds had changed the very philosophy of warfare. Traditional tactics were built on see, shoot, destroy. The Americans proved that one could win by depriving the enemy of the ability to see. The Japanese analysis was no less revealing. Colonel Takeshi Sugihara, who survived the fighting on Saipan, wrote a detailed 1947 study, The Gray Enemy, an analysis of American smoke tactics. He concluded that Japan lost not because of technological backwardness, but because of mental inflexibility. The Americans fought like merchants, Sugihara wrote. They sought the most efficient way to reach the goal with minimal losses. We fought like warriors, striving for heroic death in honorable combat. Smokescreens denied us the chance to die beautifully. This difference in mentality proved critical. Americans viewed war as a technical problem to be solved in the most efficient way. The Japanese saw it as a spiritual trial, where not only victory, but the manner of achieving it mattered. Smoke tactics also highlighted the importance of logistics in modern war. Mass use of smoke shells required a sophisticated supply system. The Americans built dedicated factories for smoke munitions and developed new methods for transport and storage. The Japanese, by contrast, never treated smoke rounds as strategically important. Even once their effectiveness became clear, Japan's industry could not quickly retool for mass production. It is a vivid example of how logistical capacity shapes tactical innovation. Another key aspect was individual initiative. The revolution in tactics began with a single lieutenant colonel's decision to experiment with smoke shells. The American military system encouraged such initiative and rapidly scaled successful innovations. Japan's system, on the other hand, emphasized strict adherence to regulations. Even when individual officers saw the need for change, bureaucracy impeded rapid implementation. This systemic difference was one factor in Japan's defeat. After 1945, smoke tactics became a standard part of American doctrine. The Pacific War experience was compiled into manuals and field regulations. Many principles developed against the Japanese were later used in Vietnam, Iraq, and Afghanistan. The experience of smoke munitions in the Pacific did not vanish with the end of World War II. On the contrary, it became the foundation for new military technologies that shaped conflicts in the second half of the 20th century. As early as 1946, American engineers began developing improved smoke systems. The main research hub was Edgewood Arsenal in Maryland, led by Dr. Robert Wilson. Wilson, a chemist who had worked on chemical warfare agents, shifted after the war to non-lethal smoke technology. The first breakthrough came in 1948 with the N99 Superfog shell. It produced 4 times more smoke than wartime models and maintained a screen for an hour. The secret lay in a new polymer base that burned slowly, gradually releasing smoke agents. But the most important innovation was the development of selective smoke mixtures. Instead of universal white smoke, Americans experimented with colors and properties. Some rounds created smoke opaque to infrared, but transparent to visible light. This was hugely significant in the age of night sights and thermal rangefinders. U.S. forces could blind enemy electronics while leaving their own observers unimpeded. At the same time, smart smoke systems emerged. The M101 round, adopted in 1952, carried simple wind sensors that adjusted smoke output depending on weather. In strong winds, it produced more smoke. In calm air, less, maintaining optimal density. The most ambitious project was Chameleon in 1955. It aimed to create smoke that changed color with the environment: white on snow, greenish on grass, yellow on sand. The concept proved too complex and was canceled for cost reasons. The Korean War, from 1950 to 1953, was the first test of post-war smoke technology. The U.S. employed advanced rounds against Chinese and North Korean troops, but the enemy had learned from World War II. The People's Liberation Army developed tactics to fight smoke screens. Instead of trying to disperse smoke, soldiers trained in sound orientation, gauging direction and distance by footsteps, voices, or equipment clatter. Results were mixed. In Korea's mountains, where sound carried far and clearly, the method worked well. On plains, American smoke retained the advantage. Vietnam brought new challenges. In Indochina's jungles, smoke dispersed faster due to humidity and constant rain. Americans had to develop tropical rounds with water-resistant mixtures. Viet Cong guerrilla tactics also posed problems. Unlike the Japanese, who fought from fixed defenses, the Viet Cong were highly mobile. Smoke screens often slowed U.S. troops more than their enemies. The greatest success came in open terrain, especially the Mekong Delta. U.S. river patrols used smoke generators to cover landings. The tactic was so effective that many special forces worldwide later adopted it. In the 21st century, the principles of smoke tactics pioneered against the Japanese have transformed into advanced systems of electronic warfare and information operations. Armies today rarely use physical smoke, but the concept of blinding the enemy remains central. The most direct descendants of smoke shells are electronic warfare systems. Modern forces generate electronic fog, radio jamming that blinds radars, communications, and navigation. The principle is the same: deny the enemy vision of the battlefield. U.S. systems like the AN/ALQ-99 and the newer AN/ALQ-249 operate precisely this way, creating electromagnetic screens that make aircraft invisible to hostile radar. This is a straight continuation of Lieutenant Colonel Murphy's idea at Guadalcanal: use screens to conceal movement. Infrared countermeasures are another lineage. Modern tanks and infantry fighting vehicles carry systems that release metallic particles or aerosols to blind thermal sights and laser rangefinders. A digital evolution of World War II's smoke screens. Most fascinating are adaptive camouflage systems. The M1A2 SEPV4 tank entering U.S. service can create a protective electronic veil that changes depending on enemy sensors, one disruption against optics, another against radar. Russian and Chinese designers have pursued similar technology, often using U.S. experience as a model. Russia's Shtora system echoes 1940s smoke screens, disrupting enemy targeting. The most unexpected legacy of smoke tactics is modern information warfare. The concept of the fog of information stems directly from the Pacific. Instead of physical blindness, armies create cognitive screens, streams of disinformation that prevent the enemy from seeing reality clearly. Operation Desert Storm. In 1991 was the first large-scale use of digital smoke screens. U.S. electronic warfare created electromagnetic chaos around Iraqi forces. Like the Japanese decades earlier, Iraqi troops remained alive but could not coordinate. The psychological effect was identical. Iraqi officers after the war described the same helplessness felt by Japanese veterans. "We knew the Americans were nearby, but we couldn't find them," recalled Colonel Saddam al-Dulaimi of Iraq's 3rd Division. The Afghan and Iraq campaigns of the 2000s posed new challenges. Taliban and insurgent tactics echoed the Viet Cong. Traditional smoke was less effective against enemies who avoided direct battles. The U.S. adapted with multispectral masking. Modern units can simultaneously obscure visual, infrared, radio, and acoustic ranges, an integrated evolution of the simple smoke shells of the 1940s. The newest systems use artificial intelligence to adapt automatically. If the enemy employs optics, they generate visual screens. If radar, electromagnetic jamming. The Ukraine war from 2022 to 2024 has demonstrated new forms of digital smoke. Both sides heavily use electronic warfare to block enemy drones. The principle is the same that Murphy pioneered on Guadalcanal: deny the enemy the ability to see and orient. Looking back over the 80 years since that September day in 1942, when Lieutenant Colonel James Murphy decided to experiment with smoke shells, the depth of his innovation becomes clear. What seemed like a simple tactical trick turned out to be a revolution in the art of war. Smoke screens changed not only how battles were fought, but the very philosophy of warfare. Until 1942, operations were built on the principle see and destroy. The Americans proved you can win by denying the enemy the ability to see. It was a fundamental paradigm shift, whose effects are still felt today. Japanese astonishment at smoke tactics reflected a deeper problem: the inability to adapt to new realities of war. Japan's warrior culture, shaped over centuries, prized personal bravery and honorable combat. Smokescreens shattered those ideals, turning war into a technical problem. Americans, by contrast, approached war pragmatically. For them, the goal was victory with minimal losses, not the display of heroism. That difference in mentality proved decisive. Where the Japanese saw dishonorable methods, Americans saw effective solutions. The Pacific War showed that technological innovation can matter more than numbers or traditional valor. Smoke shells were not complex weapons. They had existed since World War I. The revolution lay in their massed, systematic use. That lesson remains relevant. Modern conflicts are often decided less by the count of soldiers or tanks than by the effective use of information technologies, communications, and electronic warfare. The army that adapts better to new technological possibilities gains the decisive edge. The psychological dimension still matters. Soldiers who cannot orient themselves on the battlefield lose effectiveness regardless of bravery or weapon quality. Today's electronic warfare systems create the same psychological effect as the smokescreens of the 1940s. The story of American smoke shells is also a lesson in logistics. Mass adoption of a new tactic was possible only because industry pivoted quickly. U.S. factories, in a matter of months, began large-scale production of smoke munitions. Japan, by contrast, failed to adapt its industry to new demands. Even understanding the enemy's effective tactics, it lacked the technical capacity to respond adequately. It is a reminder that military power depends not only on frontline units, but also on a nation's industrial base. The most important lesson is the value of individual initiative backed by a system that supports innovation. The revolution began with one officer's decision, but it succeeded because an institution encouraged experimentation and rapidly scaled good ideas. Today, as military technology evolves at breakneck speed, that lesson is especially urgent. Armies that swiftly absorb new technologies and tactics will gain decisive advantages. Those that cling to tradition risk ending up like Japanese soldiers wandering in the gray fog of American smoke. Perhaps the deepest legacy of that distant Guadalcanal experiment is the understanding that in war there are no honorable and dishonorable methods, only effective and ineffective ones. Murphy wasn't trying to revolutionize warfare when he told his mortar crews to fire smoke. He was trying to save his soldiers' lives. It was precisely that pragmatic logic, seeking the most effective solution instead of obeying inherited rules, that became a key to American victory in the Pacific. And today, as the world faces new challenges, the lesson remains vital. The smoke has dispersed, but its shadow still shapes modern military thinking, reminding us of the power of adaptation, the importance of technological innovation, and the enduring need to think anew in a changing world.